Good afternoon, dear colleagues. My name is Artem Sukhov, and today I will present to you our solution of problem number 12 with names resonating glasses. When we take two glasses between your fingers, they sometimes emit a particular and containing a frequency sweep sound, and we need to investigate this phenomenon. So we obtained this sound. You can hear this. And observed a multi-collision of two glasses with characteristic frequency, sweep sound, and role of the finger between glasses is very important, how you can see on the second video. We recorded the sound and created the spectrogram of sound in Python. We can highlight two areas of effects. An area where we can distinguish all of the collisions, and the second area where we cannot distinguish some different collisions, but we can describe a frequency sweep. For this, we describe our experimental setup. We change our fingers for ups to push glasses to each other. Finger between glasses substituted by rods, and our launch setup provides the initial symmetry of launch. So we filmed the process by high FPS camera with 6,000 frames per second, and we took into account the parallax effect. Also, we record the frequency sweep sound by the microphone and external sound card with 44 and 100 Hertz discretization. And finally, we can check and measure contact time of two glasses by oscilloscope because contact of two glasses completed the electrical circuit. For this, we sputtered conductor onto glasses, and thickness of this layer about micrometers, and this layer did not affect the dynamic of the motion, and the virus is very light, and we can neglect the elasticity coefficient. We set the problem, and we can describe the firstly multi-collisions between two pendulums. Okay, initial motion we can describe by two pendulums, force acting on each other, equivalent to initial strain of wraps and strain oscillations by stretching. This is simple harmonic motion, but pendulums collide before equilibrium state. And time between collisions we can write by expression of the slide. There is omega. Omega is constant angular speed. X is coordinate of collision, and x maximum is amplitude, current amplitude. After the collision, we can obtain a velocity from restitution coefficient. This is coefficient is constant for all of the collisions, and we check this by a high FPS camera. We can measure velocity before collision and after collision. And so time between collisions decreases from collision number, but the theory is slightly higher than the experimental values, and we need to take into account our resistance. So our motion is non-harmonic, and we can describe motion Newton's law in area of application small angular model and Hooke's law with turbulence R resistance model, and the theory describes current well as seen in the video. Also, we change rod radius, and the higher radius value, a higher time of all collisions we can see, and theory describes experiments well. And for all experimental points, we have 5 experiments per 1 point. Also, we change the initial elasticity force, and we change this by changing the wraps count. Okay, now we can describe motion by contact time, but contact moment of two glasses, and there is next stage. For description of glasses contact, we use Palmgren's cylinder model, and contact force have elasticity nature, where stiffness parameter determined by modulus composition and contact length. Also, this model, in this model, we correction on a non-linear elasticity and Poisson coefficient and elastic modulus we obtain from the experiments. So by Newton's law application with corrections for this model from this article on the slide, we can derive maximum relation relative distance between glasses, also maximum force acting in the process and time of contact, and we can assume that force changing have a science law. Okay, we can calculate contact force, and from the dynamic solution we can calculate velocity after collision, and also restitution coefficient is well predicted by our theory. After that, we compare contact time of two glasses and compare this time with measurements from digital oscilloscope data. Also, this model is compared by finite element methods before us in the literature on the slide. And velocity before collision affects the contact time, but at low speeds we have some constant value, and this is important for next investigation. So we finally described the mechanical motion. Now we need to investigate acoustic of our system. Firstly, we calculate agent frequencies for one glass, and from the solution of flexural Waves law with attenuation, we modulate this system in COMSOL. We have once attenuated experiment for one glass, and how we can see the frequencies converge well in the simulation and in the experiment. But we consider the original system with two oscillated glasses, and we observe another frequency that's repeated in different experiments for the same system. What is this? It is specific frequency of for system, because after the moment of contact we have area of low pressure between glasses and area of high pressure on the sides. This fact checked in the experiments and in the simulation, and this frequency proportional to the sound speed in air divided by diameter of glass. And we check this ratio in the experiment with different diameters, and model works correctly. So we describe frequencies allocated for the system. Now we need to explain the final sounds that we can hear. Let's remember the problem with the fact that our sound from individual collision goes into in a rising tone. We describe all of the mechanics, and now we can describe also frequencies changing by contact time and time between collisions. After that, we can change window size of Fourier transform for spectrogram, and we can see that the time of changing area is different for different window sizes. So we can explain this by that each collision is delta function. One delta function per window is rectangle, but periodic delta function structure per window is direct comb, and result of this frequency transform is frequency of periodic structure and their overtones, and the window time affects the spectrogram, and we can describe this by our theory and our model. Also, we carried out acoustic experiments, and after that we can assume that the window size of human ear about 500 units window size. After that, I can say that experimental setup is constructed. Also, we can describe motion of our glasses by the time. Also, we can predict contact time, and also we can hear not only agent frequencies but also specific system frequency, and you can hear.
Thank you. We ran out of time.
My name is Juan Manuel. I'm going to be the opponent of the problem number 2, resonating glasses. And I would like to emphasize the statement of the problem first, before I'm going to do the presentation. The problem states that when you take 2 glasses between your fingers, they sometimes emit a particular sound containing a frequency sweep. And the only question is investigate the phenomenon. So first, I'm going to remark the strengths of the reporters. The presentation was extremely good. I'm going to say that the first strength is that they make a proper statement of the involved parameters on the phenomenon, and that proper statement of the involved parameters was made at the beginning of the presentation, and that makes it easy to understand what are the way they took to make the solution of the problem. The second strength is the extremely precise experimental devices that they use in the experimental setup, the camera, the microphone. That experimental setup is really precise. The third strength is that they use the pendulum analogy, and they use the simulation of that pendulum analogy, and that's very important here. The first strength is that they take into account the amplitude change in that pendulum analysis, and it's very important, and it's a key parameter here, the amplitude change along the pendulum analogy, and they take into account that. The next strength is that they use finite element modeling in the deformation simulation, and the simulation in console was quite good, and they simulate different type of glasses, and that's very important here. Finally, they make proper explanation of the frequency presented of the system and the clarification of that frequency that appears in all the graphs. Something extremely important here is that they use the delta Dirac approximation. They use that in order to remark the importance of the ear in this problem, and that was extremely good. And they use multiple ways to show the solution. They use a theoretical explanation, they use experimental devices, experimental data, and finally they use a computing simulation, and that's extremely important in this type of problems. Now we can move to the weaknesses of the problem. First, I think that there are some saturated slides. There's too much information, too much GIFs, text. If you can reduce that, you can improve the speaker time, and that will increase the proper explanation of what you have found. The second weaknesses is that we think that we need to discuss later too, the effects of groups against fingers, because in the problem statement, the fingers are very important here. And we think that changing that fingers with groups or with other elements would affect the damping in the frequency of the restitution coefficient, for example. We think that this is a weakness here. I think also that there wasn't clear the relation between the multiple models that you use. For example, you use a pendulum with some frequency and you calculate that from the model. And I'm not sure if it is related with the frequency in the delta function that you use it to model the ear. So that's very important. Finally, the impact of the natural and harmonic frequencies of the glass, the material types and the glass dimensions wasn't clear, that impact of the natural frequency of the glass and his harmonics. And finally, due to the time, the conclusions were not clear, so we can see them clearly in order to see what was the final solution to this problem. Now, the discussion points that I would like to discuss in the next 5 minutes are: first, we talk about the phenomenon again, and I need to talk about the effects of the fingers and how can you be sure that changing them are not extremely important in this problem. The second one is the importance of damping for the frequency sweep. And finally, the characterization that I think is very important to include is the relationship between the natural frequency of the glass and the frequency of the sweep spectra, because you mentioned that common frequency that we can see on the graph aren't the natural frequency of the glass. So we need to know where the natural frequency of the glass and the harmonics of this sound will be included in in your solution, for example. So that will be all by my way. So I can move to the discussion, please.
Okay, can I show my presentation? Can you stop your? Thank you. I'm afraid, can I clarify for you different models, because you think that I have many models for different situations, but I have many models for one big model.
I wasn't saying that. Sorry, just to clarify, it wasn't clear how are they connected.
Okay. Well, this is a very big bridge from first slide to the final. And firstly, we calculate a motion of the balls, and we can calculate the time of the contact, initial time of contact.
Okay.
We have pendulums, contact.
Yes.
After that, our model about contact moment. From this model, we can calculate time of contact after that. And again, we have multi-collision model.
Okay.
After that, in the acoustic plane, we have system frequencies. After the collides, we have full spectrum of frequency, but some frequencies in the spectrum are stable for the long time because it is frequencies of the system. Yeah.
Sorry, I have a question here. While are you doing here? In that simulation, do you include different type of materials for the glass?
Yes, we can. But this is simulation for our glasses for our material. But we can change this. But we can change this. Yes.
Okay, perfect. Continue.
After that, we observe the very interesting frequency, specific frequency for oscillator. It is frequency by this stable wave, not the eigenfrequency, but specific frequency for the system. And after that, we can simulate the signal from the time by collisions with a pressure spectrum by the contact force. In the simple model, we have delta functions at moment of the impact, but in the very difficult model, we have signal per each collision, but time between these collisions and these signals decreases by the number of collisions, by the time.
Okay, now, thank you. I can see the connection now. Thank you.
Yes, okay.
Thank you very much. We can move on the discussion if you think that the changing of, we don't make the experiment with the fingers, it's very important here because we think that the fingers and the damping due to that is very important.
Okay, damping is very important. You say about wraps in our experimental model.
Yes.
How do you think it is it correct that we have wraps against fingers, and what is difference if you think that not?
Because with the fingers you have more contact area between the glasses, and that will dampen some time of frequency that you aren't able to detect.
I'm sorry. Can you?
So the idea of the fingers, maybe they include the damping of some frequencies that are important in this phenomena. And with the rod, you change that. Do you consider that?
Okay, but we change the ramp numbers, and we can see that time of collisions decreases, but it is not effect of some attenuation. I think that it is effect of collide position, because our pendulums collide before equilibrium, and this is time equilibrium from equilibrium to impact is increases by current amplitude, and amplitude decreases by the collision number, because we have restitution coefficient.
Okay.
And it is my point of view.
Okay. Okay, perfect. I have a question for you. Do you consider that you use metal glasses? Yes?
No.
And we use glass and metal.
Yeah, sputtered by metal glasses.
Okay. And in the rock one, you use I think that something that is needed to improve it is the change on the type of material that was made the glass, because you then take into account the natural frequency of your glasses and the harmonics, and changing that material will be something important in this solution. I think
it is important, but not so interesting, because we have different agent frequencies. We have different stable frequencies for the material, but the final sound is about signal from our system, from a motion of our system. It is about signal from motion, yeah, not about material.
Okay, perfect.
So,
we are moving now to the teams discussion.
Now teams can
Yes.
connect.
Sorry.
Connect.
We have a question.
Can I add a comment?
Wait.
Sorry.
We have a question here.
Okay. I have a suggestion. I think that the use of the rod is a very good idea in order to control that. But I think that maybe in order to improve the solution and experimental setup, is also possible to recover the rod with a material that simulate a little bit better the fingers, because the finger have like a more inelastic collision with the glass and can absorb more energy. So I think that the idea of the finger is that maybe can change your time for the collision that you propose on your model. That is, you can try to stimulate the fingers, and I think that this idea can improve the solution and also the model in terms of
I think it is a question about our model, and for the fingers we have different forces, but I think that RAPS is a good way for accept human factor. Maybe we can change RAPS for force that depends on the time, maybe.
Okay, perfect. I hear that your teammate has a comment.
Yeah. I want to make a comment about making the glass with air of copper. We try to decrease as possible the changing of the sound. So we make the size of the layer around 1 micrometer, and the diameter of the contacts was around 100 micrometers. So we decrease the effect on the system as possible.
Okay, we have another question here for the report.
Yeah, we are talking in discussion about the finger or the rod, but there's a question that I understand you made a chain of methods, yeah, the movement, the contact, then the propagation of sound. But in the simulation, I see that you study the propagation, but you don't take into account in this simulation the fate of or the rod or of the finger or whatever is sustaining the glass. So how do you take in your model these deformations into account?
Deformations in the rod? Yeah.
No. The deformations are different if we collide one glass alone.
Can you show the simulation?
Yes, the video of the console simulation.
Simulation of
the console simulation. The console simulation.
Okay, I can. It is about eigenfrequencies.
Yeah, but that simulates the glass, the movement of the glass.
This is this is movement of the glass. Yeah.
Yeah, so you can study the propagation of the frequency, the sound. But my question is, how do you input in this simulation the physical restriction or of the finger or the rod or whatever is sustaining the two glasses?
It is another frequencies. I'm sorry. It is frequencies characterizes the glass. Yes, also we have frequency characterized by the rod, but it is very low amplitude frequency, and we can see this frequency on the slide. in the slide. Also, we cannot see frequency. We can see frequency of routes because it is the same frequency. Yeah.
Okay, I have a question for you. What do you consider is the most important effect in order to hear the frequency sweep in this problem? You explain a lot, but I want to see what you consider is the most important one.
Why can we hear frequency sweep? Yeah.
Yes.
Because model of our ear, it is about wavelet transform, but in simple considerations, it is about fast Fourier transform. We have some filter in our ears, and window size of this filter affects the time of frequency sweep, and this is clearly shown on these graphs by changing the window size. And also we carried out psychoacoustic experiments and has different results for different persons of
have you simulated the sound numerically, the sound you should get as a result?
Yes, yes, on this slide. Can you hear this?
And have you tried to compare this sound by any means to the real sound?
Yes, like this.
Not just by ear, but
like this, yes.
So this is the numeric simulation in the
yes,
and the theory around it. Oh,
no, not
the experiment around it.
Yes.
Is there any questions from other juries? Yeah, Adrian, I see your hand. You can unmute yourself and ask.
Quite a few questions, but so my first question would be: is there? You speak about the rebound, the time of flight between rebounds, and then they also investigate the contact time. But I wonder, is there a crossover? Do you have rebounds until the end, or is there some point where the glasses stay permanently in touch? And is anything happening at that point?
Okay, you ask about the situation when our glasses is unstable in moment of contact, yes?
Well, eventually the energy dissipates, and so at some point maybe there is not even enough energy to take off anymore. So the glasses
yes,
contact and go on vibrating.
Yes, in this point we have saturating of the frequency, and we didn't investigate this, but I think that it is a real situation. This situation is real, and for this analysis, we haven't. We have only the video and the frequency by the microphone, and this effect neglectable. It is effect of the time after. I don't know. At this point, can you see my mouse?
Yes, I can. Okay. Okay.
This is effect of this. It is very low pressure. It is very low amplitude.
I see.
Rafael, please, your question.
Yes, I have a question for Team Russia. If you change the air density, would you expect to see different results, and how different?
Yes, we can describe different results because we have frequency that affects depends on the air density, because depends on the speed sound in the air, and also all of the acoustic and pressure and motion also is different for this situation, because we have different resistance forces from the outer and outer conditions, and also we have we have different attenuation of the waves in the air.
Thank you.
Is my answer.
Yeah, I see the hand from Jürgen. Please, your question.
To the experiment from Russia, does it any impact where to position your microphone on the experiment?
Yes, yes. It is. It discovered and it investigated before us. We have different waves from different sites, because we have different wave propagation in the medium, outer medium, like air. And we have different sounds, but we can predict all of the sounds by wave propagation, and this considered, this investigated by many peoples in the literature. It is not about the sound, but this is a real effect.
Thank you for the answer. And last short question from the Alexei, please.
Could you please show slide 29?
29, yes, I can.
Here we have two areas with distant collisions and frequency sweep. How clear is the boundary between these two areas? Was it put just by eye, or is there a clear?
This is not clear, but we can predict some area by simulation with different window sizes for fast Fourier transform, because it is problem of mathematics. This is collisions. This is collisions after that time, but on the spectrogram and by the mathematical apparatus, we have different results for spectrogram, because we have different window sizes, and it is amazing because it is a question about mathematics. Physics application mathematics.